I'll be covering stress transformations in 3D. So we had previously discussed stress transformations um, for plane stress type situations where there's only stress states that are in plane to the system, such as sigma xx, sigma yy, which are the normal stresses in the xy plane, and sigma xy, which is the shear stress in plane. The other three stresses were assumed to be zero for the 2D plane stress transformation that we had discussed previously. Why study stress? We learned that a stress is a quantity that describes or is a quantity that reacts and explains that reaction of internal force like quantity inside the body of material. It could be a wing, a diving board, a launch vehicle, an aircraft, a tool, a wrench, a car. The stress varies across a system, across a structural system. And that stress inside the body varies to satisfy, and it varies in such a way that it satisfies the equations of elasticity that we had discussed in a previous lecture. But that stress quantity is reacting in a pointwise manner. The external loads are applied to the system. You can only apply external loads to the system by applying traction loads on the surface, body forces, and acceleration. So we learned about the idea of stress, and then we studied how to determine this, the stresses in a particular plane of interest that could be oblique to or an oriented in a direction that's not aligned with the Cartesian system. And we learn about the idea of principal stresses, which is a plane, an oblique plane of some kind, um, whose orientation is such that then the tractions are normal to that surface, but there's no shear stresses in that plane or tangential stresses to that plane. And that concept is actually quite interesting and useful and can be used to predict the failure of brittle material. We've also covered the idea of stress transformations afterward. And now in this lecture, we're going to be covering
What what I was discussing then is that we'll now move forward with the idea of stress transformations in 3D. And that is useful because a lot of the systems you may encounter are three-dimensional structures. So let's dive into that topic today. So here, what you see is an axis, a coordinate system that's 1, 2, 3. I've also used XYZ, so that can also be used here. But the idea is I would like to understand what the stress states are. So say I know the stress states sigma 1, 1, sigma 2, 2, sigma 3, 3. I change the convention, but it could be sigma XX, or so instead of 1 is X. So sigma XX, sigma YY along the 2 direction, sigma ZZ along the 3, and then you have shear stresses acting on this structure. But I'd like to know what the stress states are in a different orientation. Say I want to know it along the 1 prime, 2 prime, and 3 prime. To really understand how to do that properly, it's important to understand how to calculate the transformation matrix. And that transformation matrix is the one I'm showing here in the bottom right. In essence, this is what represents is the direction cosines. And for example, I'll show you an example. So say in this first row and first column, I have the cosine between the 1 prime and the 1. So this cosine has to be calculated. You basically need to know the angle of the 1 prime axis and the 1 axis here. And if you know that angle, then you can calculate that cosine. And then similarly, I can go to the next one. I need to know the angle between the cosine of 1 prime and the 2 axis. And so if I know that value, then I can plug it in and calculate the cosine of that. In this particular example of the one I have drawn, you can see that the rotation that was performed was about the 3 axis. So therefore, the cosine between the 3 prime axis and the 3 is 0 degrees because they're aligned, they're in the same orientation. So the angle between the 3 and 3 prime is 0. So the cosine of 0 is 1. So we can fill that out, is obviously 1. Another example for the picture I'm showing here, the cosine of 1 prime and 3. So you can see here, the 1 prime is in the plane of 1 and 2, while the 3 axis is perpendicular to that plane. So therefore, the cosine of the 1 prime axis and the 3 axis is 90 degrees. So cosine of 90 degrees is 0. And so you'll find that these two are 0. The position row 3, column 3 is 0 here. And then these other two are also 0. But this matrix will need to be calculated for us to be able to do the transformations in 3D successfully. So let me give you an example that's practical. So say that I know the stress states in the 1, 2, and 3 coordinate system, which I've been using X, Y, and Z earlier. But I think it's important to understand different conventions that different books may have. In this example, I'm stating to you, and you know this information is known to you, the problem statement will alert you what is being looked for. So in this case, the problem statement stated that the angle between the 1 prime and the 1 axis is alpha. And so in that case, that makes it easy, right? So I can draw all this here so I can have it all visually clear to me. So you can see the 1 axis is pointing downwards, the 2 is pointing to the right, the 1 prime is pointed that way, so that the angle between the 1 prime and 1 is alpha. If that angle is alpha, then the angle in here will be alpha minus 90, because this one is 90. So alpha minus 90 plus 90 should be alpha. So you can see that the angle between 1 and 1 prime is correct, is alpha. So that's the angle I'm calling alpha. And from there, you can calculate the other angles you're going to need using just pure geometry to be able to fill these out. So in the previous example, I filled for you out the 3rd column and the 3rd row completely, because we saw that each of these are 0 because the 3 axis is perpendicular to where the rotation is occurring. So nothing's going on there. So 0, 0, 1, 0, 0. We've done that already in the previous example. So with that known, we can fill the rest of them out. So cosine, the angle between 1 prime, the 1 prime axis, and the 1 axis here, that angle is alpha. I'm telling you what it is. So obviously that's alpha. Then that will be specified, will be 45 degrees, 30 degrees, whatever it is. In this case, it's known. So I didn't give you the value, but give you a variable. So that's cosine of alpha. And then I have to calculate the angle between the 1 prime and the 2 axis. So that's why this diagram is useful, because you can use geometry to figure stuff out. I did it in advance, but I invite you to try it at home, because just observing what I'm doing may not be sufficient. Since the angle between 1 and 1 prime is alpha, and the angle between 1 and 2 is 90, then it has to be that the angle between 1 prime and the 2 axis is alpha minus 90. There's no other choice. So that tells me that this is cosine of alpha minus 90, which if you use a calculator or you use Mathematica, or you remember the identities, you find that that's just sine of alpha. Very similarly, then I can find the cosine of 2 prime axis and the 1 axis, and you find that that angle is 270 minus alpha. Well, if you do the calculation, you'll find that that's minus sine alpha. And then finally, the angle between 2 prime axis and the 2 axis is actually alpha itself. So you can go ahead and see that for yourself, and you plug it in and you get cosine alpha. So that's the procedure that you follow to be able to fill this transformation matrix. And if you're able to use, you're able to fill this direction cosine matrix, which is your transformation matrix, then you'll be able to do the following steps. So then I'll go ahead and show you the formula that needs to be used. So in this particular example, I gave you find Q, right? This transformation matrix. What you do then is to calculate the stress that you want in the new coordinate system. In this case, is in the red, and you make it equal to Q. So you take this matrix here, Q, you multiply by the stress state that was given to you in the problem statement, and then you multiply by the Q, but now transpose. And when you do this multiplication, you'll find the stress state in this new coordinate system. Now, why is this useful? Let me give you an example where this is actually quite useful, okay? This is going to make sense to you when I explain it. One of the reasons that these calculations are useful is, for example, in the prediction of failure of composite materials. In composite materials, you know the loading environments applied to maybe a composite system that's aligned with a Cartesian system. So maybe you know the load in a pressure vessel, or you know the load applied on this edge, for example, but you're able to take the stress states, calculate the stress states first in this global Cartesian coordinate system, and then if the fibers were oriented like in the white, and I wanted to know the stress along the white, so for example, line, for example, which represents the fibers, I wanted to know, I know the strength of the fiber direction, of the composites in the fiber direction. So I know the strength of the fiber in the composite fiber direction. So say I know what that value is. Then if I know the stress states in this system, I can then transform it so that I know the stress along the 1' axis. And if I have that value, then I'm able to take that and compare it to the strength of the material. That is just one application where it's valuable to learn how to do transformations in three-dimensional theory. So once you calculate Q, you plug it in here and then do this multiplication. So you have to multiply the matrices 3 times to get the stress state in a new coordinate system. So now the stress that I get are going to be such that they're aligned with the prime axis, which is in red. So then I know sigma 1 prime, I know sigma 2 prime, which is aligned with the x2 prime direction, and so forth. It turns out that everything I've done so far will match what I showed you in a previous lecture. If I do a transformation into these so that everything's rotating about a third direction, that's pretty much what I did in the previous lecture when I did 2D transformation. So the Q is calculated like that, and sigma prime will be equal to this transformation matrix times sigma, the stress state provided to you in the Cartesian coordinate system along the x and y, multiplied by Q transpose. When you perform this multiplication in that order, you will get the very same equations I showed you in a previous lecture. And these equations can then be rewritten in this manner for convenience. If you're able to do this multiplication, then, and so if you're able to do so, if you're able to do this transformation like this, multiply all these things out and get this answer, it's going to increase your confidence because you're doing it in a very different way than you've done it previously. And so you're going to learn about a different method in doing these transformations in a more systematic way. With that, we will then now move to the next lecture.